Let's take a look at how to define some standard functions over lists using the template that we developed in the last segment. Let's think about how we might concatenate together a whole list of lists. So just to give you an example, if we have the list which has three lists inside it, the list 2.1, the empty list, and list 1.3, when we concatenate those together, we get the list 2.1.1.3. So what should we put in to our template? What do we get if we concatenate an empty list? Of lists, well, we get an empty list. There are no elements in any of the lists because there are no lists. What about concatenating a list whose head is X and whose tail is X's? Suppose we've concatenated everything in the tail into a single list, and then we have this other list X that needs to be joined. What we do is join together X and concat of X's using ++. And so what we write is X ++ concat of X's. Let's try that out in an evaluation. Let's try concat of the list 2.1, the empty list, and the list 3.1. Which equation applies? Remember, if we do a pattern match, here is X and this is X's. So this becomes the list 2.1 joined to the concatenation of the empty list and the list 3.1. But what does this become? What does that concatenation become? We have 2.1, and then again doing the pattern match, here is X, here is X's. This becomes X, the empty list, ++ concat of the remainder, which is the list with just 3.1 in it. So it's a list containing a single list. Let's scroll up a bit more if we can. Give us a bit more space. So we have 2.1 ++ empty list ++. Now again, doing the pattern match, here is X, and now X is the empty list. So this becomes ++, whoops. ++, concat of the empty list now. And then we can use the first clause, which says reminder concat of the empty list is the empty list, to give us 2.1 ++ empty list ++ 3.1 ++ empty list, which gives us 2.1.3.1. It has indeed joined all those lists into a single list. Now, I've been assuming that ++ is already defined, and it does as we should expect. Let's now take a look at how we could define ++ for ourselves. And for example, if we have the list 2.1 and the list 1.3, that shows those two should join into the list 2.1.1.3. Now, how can we fill in this template for ++? Now, we've got something slightly different going on here. We've got this we're doing the primitive recursion over the thing to the left of the plus plus, and we just have a constant undefined y's on the right. The reason for that is because we build lists by adding elements on the left, and so we will build up our result by adding things on the left, and so it makes sense for us to do recursion on the left rather than on the right. And let's just see how this works out. First of all, what is the empty list joined to the list of y's? Well, that is simply y's. But what about the second case? We want to join a list whose head is x and whose tail is x's to the list y's, and we're already given x is the tail and y's joined together. We've already got x's plus y's. How do we build the list with that extra element in front? Well, the answer is we simply put x on the front of x's plus y's using cons. So we write x cons x's plus y's. Now, what I'd like to do is show that example in practice, simply so that we can see it, how it works in practice. So let's do that now. Okay, let's look at the example 2, 1, plus, the list with just 0 in it. So y's throughout this is going to be the list with 0. Let's take a look at now which equation applies. Again, here is x and this is x's. So this becomes 2 stuck on the front of 1 plus list with just 0. Now again, if we look at the inner plus, here is our x this time. Our x is 1. Our x is the empty list. And so this becomes 2 stuck on the front of 1 stuck on the front of empty list plus list with 0 in it. And now, if we look at the equations, it's the first equation which holds, and that says this is 2 on the front of 1 on the front of the list with this 0 in it. And that, if we resolve the conses there, we get the list 1, 0, and then finally we get the list 2, 1, 0, as we would expect. So you can see there that is behaving exactly as we would hope. It's joined those two lists together using the recursion that we defined. As our next example, let's think of the question of membership. What we're trying to define here is we've got a function elem that takes an integer and a list of integers, and it returns true if that first integer is a member of the list of integers, and false if not. And we have to think about, again, we will do recursion on the list. So we have two cases as ever. We have the case where the list is empty. Now, if there are no elements in the list, then the answer is false. But what about the answer in the case that the list is x cons x's? Now, if you think about it, that list has one element x and then everything else is in x's. So there are two ways that y could be a member. It could be x itself, so it could be that y equals x, or it could be that y is a member of x's. That's the only way y could be in the list x cons x's. It could be x equal to x. It could be a member, could be an element of x x's. And so either x is y or y is an element of x's. So we can write that in Haskell as x equals y or element y x's. Let's just see how that works out in practice. Let's look at the example of elem 1 in the list 2, 1. Now when we do the pattern match, here is x, here is x's. So that becomes x equals y, so that's 2 equals 1, or elem 1 x's, which is the list with just 1 in it. Now, as we go along, we can, if you like, simplify this, and so we can say, well, 2 equals 1 is false, or elem 1, 1, and so that false or anything is the anything. So that becomes elem 1, 1. List. Now, using pattern matching again, here is x, the remainder is the tail, the empty list is x's, and so this now says 1 equals 1, or elem 1 x's, which is the empty list. Now again, we can see that this is true, 1 equals 1, or anything, and in fact true or anything evaluates to true. So we see here the answer that we would expect. This evaluation has given us that 1 is an element of the list 2, 1. You could try for yourselves to check that the result of elem1 of the list 2, 3 is going to be false, and by a similar chain of evaluation. As a last example, or a last couple of examples, let's look at map. You remember map was that wonderful general function we have seen earlier, which takes a function from A to B, a list of A's, and returns a list of B's by applying f to every member in the list. Now, again, the empty list case is simple because if there are no elements in the list, the result will be an empty list again. But what about the case where we have a list x cons x's? The first thing in the list is x, the remainder of the list is x's. And suppose somebody gives us the result of map fx's, so that's f applied to everything else in the list. How do we work out map of f on x cons x's? Well, the answer is we apply f to x and stick it on the front. So we have this pattern that map f on x cons x's is f of x, cons map f x's. Really nice, straightforward definition. And I'll leave you to try that out with an example yourselves. Finally, let's look at filter. Filter is the function that takes a list of A's, returns a list of A's, and what it does, it returns only those A's for which the property, the first argument, returns true. So again, filter, if there are no elements in the list, the result of filtering is the empty list. Now suppose we've got filter p of x's. That's all the list of everything in x's that has the property p. What about filter p of x cons x's? Well, the question is, should we add x to the front or not? And the answer is we add x to the front when p of x is true. So if p of x holds, we put x on the front, otherwise we don't. And so here we see that defined. We have a guard. If p of x is true, the answer is x cons filter p x's. We include x. Otherwise, it's just filter p x's. And again, why not try that out with an example for yourselves? So we've seen here the template applied in a number of different cases, giving us definitions of concat and plus and elem and map and filter, those crucial functions from the standard prelude. What we do next is look at some examples where the recursion has to be rather different in order to make the definitions.